Welcome to Maths with EJD. We are talking about numerical analysis, and in the previous video, I had considered the bisection method, which is a 2 points method for finding roots of nonlinear equations. So, when we talk about nonlinear equations, right? Nonlinear equations. So we have two broad categories of solution methods. We have the 2 point methods, 2 point methods, and we have the 1 point method. 1 point methods. So under the 2 point methods, we have something like we have the bisection method and we have secant method. Secant method. So under the 1 point method, we have what we call the fixed point iteration, fixed point iteration method. And then we have Newton-Raphson. Newton-Raphson. Okay. So in the last video, we had considered bisection. So right now, the next deal is about about the secant method. So let's get on that journey and enjoy the process. Let's go. Okay. So secant method. Secant method. So we're going to see the definition, the derivation, and then we'll solve the same problem we solved using the bisection method and see how fast, which one is faster in comparison. So the second method is a numerical technique. Is a numerical technique for solving nonlinear equations. Nonlinear equations. That's equation with power 2 upwards, or equations that are not even polynomial in the first place. So nonlinear equations, for nonlinear equations, right? So it is faster, okay? It is faster than the bisection method. How do we know if it is faster? So we solve the same problem using the different methods and see which one gives us the faster result. So, which one, in how many iterations we get our results, right? If the one that requires fewer iteration, given the same tolerance limits and the same problem, would be said to be the faster. So it is faster than the bisection method because it approximates the the derivative of the function using two initial guesses. Using two initial guesses. Okay. Now, this can lead to faster convergence. This can lead to faster convergence. But the method requires good initial approximations. Good initial approximations. Okay, so that said, can we look at the derivation? How do we derive the secant method? It's a very beautiful process. Imagine you have a graph like this. You have the x-axis there, you have the y-axis here. This is the origin. So imagine you have whatever, let's say something like this. Does this work? Let me make something better. So let's say okay, trying to get a very nice one. So imagine that you have a graph like this. So, and then imagine that you have a straight line cutting across this way. And, you know, um, this is a point. This is point x naught, which will correspond. Of course, this is x naught, f of x naught. Okay, we have that point. And this other point is x1, f of x1. Okay, so if you have something like this, so this line now is what we refer to as a secant. And this is how the whole process goes. Imagine that you have, so I mean, given a nonlinear function, uh, okay, to find the root of a nonlinear function, f of x, that is, we need to find x such that f of x is equal to 0. Okay, that's what it means to find the root. So the next thing is, suppose we have two initial approximations, x naught and x1, just like what we have up there. So we see x naught. So let's say this is, so we are looking for root, right? So they have this x naught and x1. So these are just approximations. So this is x naught and this is x1. So these are the initial approximations. Okay. So we have this such that, okay, x1. Okay, second. So we have this such that f of x naught is not equal to f of x1, because if they are equal, then the whole thing breaks down. So such that f of x naught is not equal to f of x1. So it is notable that the second line the second line passing through x naught, comma f of x naught as indicated above, and x1, comma f of x1, those 2 points indicated above. So that this point, and this point. Okay. So the second line passing through x1, I mean x naught, comma f of x naught, and x1, comma f of x1 can be used. We can actually use that line, can be used to estimate the root, Okay. So first of all, for that line, we can find the slope, right? I mean, if you have at some point down the line, I'm going to be talking about coordinate geometry. But if you have points x naught, f of x naught, x1, f of x1, the slope m, so the slope of the line m is actually given as just like y1 minus y naught, that's f of x1 minus f of x naught, divided by x1 minus x naught. This is the formula for slope. Here f of x1 is like y1, f of x naught is like y naught. Okay. Again, also the equation of the second line can be expressed as, so for the equation of a line, right, we know it's actually supposed to be y minus, let's say y1 minus y, or let's say y minus y1 all over x minus x1. That should be equal to the slope, right? And we already have the slope up there. So in that case, we can put all of this together so that we now have y minus y1 is f of x1 all over x minus x1 is x1, of course. And I mean, the slope, we already have m as the slope. So this is m, and this is the m defined, right? So that is equal to f of f of x1 minus f of x naught, f of x1 minus f of x naught, all over x1 minus x naught. So we have this going that way. Now, all we need to do then is we now need to state that since f of x, of course, we know f of x will be y in this case, since y1 is f of x. And so since f of x is equal to 0 and that is equal to y, right? So that means that when we come down here, instead of y here, we have 0 minus f of x1 all over. So it's more like we're solving that equation. So x minus x1 equals f of x1 minus f of x naught all over x1 minus x naught. So now this is gone to 0. So we have minus f of x1 all over x minus x1 equals f of x1 minus f of x naught all over x1 minus x naught. So that's the idea of secant. So now all we just need to do is to make x the subject of formula. So we can now get something. So this is now what we are looking for. This x is what we are looking for. So now we can cross multiply. If you cross multiply on the so if this multiplies this, we have f of x1 minus f of x naught, all this now into x minus x1, and that is equal to minus f of x1 into x1 minus x naught. Okay, so don't forget this is the x we are looking for. Okay, so now we can divide through by this guy, by this one. We can divide through by this so that we have x minus x1 equals minus f of x1 into x1 minus x naught all over f of x1 minus f of x naught. So it's things are gradually coming together. So we can simply just say x is equal to, so x1 can go to the other side. So we have x1 minus f of x1 into x1 minus x naught all over f of x1 minus f of x naught. Okay. Now we can take it that this x here is the same thing as the next x, which is x2. So x2 now will be equal to all of that. So we say that x2 is equal to x1 minus f of, okay, I guess I want to color code at this point. Yeah. So we have x2 equals x1 minus f of x1 into x1 minus x naught all over f of x1 minus f of x naught. So generally, if we generalize that formula, right? Generally, we now have the second formula. Generally, the second method formula can be given as xn plus 1, that's x2 now equals x1 will now be xn minus f of x1, that's f of xn into x1 minus x0, that is xn minus xn minus 1, then all over f of xn minus f of xn minus 1. So this becomes a general formula for secant method. But there's a condition, right? There's a condition to that. If not, the law breaks down, the formula breaks down. So it is important to note that f of xn must not be equal to f of xn minus 1. That's what we started with, that f of x naught must not be equal to f of x1. So with this, we have derived the formula for the secant method. So I guess the next thing is to go and talk about the steps. How do we use secant method to solve problems, to find the root of an equation? So let's go for that. Steps in secant method. Steps in secant method. So we have this. So the first thing we want to do is we need to choose, right? Choose two initial approximations. Choose two initial approximations, x0 and x1. We saw that when we're explaining up there. Then two, use the second formula. Use the second formula iteratively, like keep iterating. Now the question is, how do you know when to stop? Uh, the solution is considered valid. The solution is considered valid when the absolute value of xn plus 1 minus xn is less than the tolerance limit. Okay, it's less than tolerance limit. It's less than epsilon, where epsilon is equal to tolerance limits. Tolerance limits. So that gives us a guide as to how far. So the more accurate result you want, the smaller would your tolerance limit be. Okay, so let's head for an actual solution using, let's solve the same problem, right? Using the secant method. So let's go for that. So example, find the root of f of x equals x cubed minus x minus 2 in the interval 1, 2 for epsilon equals 0.01. That's 10 raised to minus 2. So that's what we need to do. So to go ahead with that, so solution. So we already know the steps, so we just follow those steps. So first of all, we know the formula is xn plus 1 equals xn minus f of xn into xn minus xn minus 1 divided by f of xn minus f of xn minus 1. Okay, so with that done, let's clarify what are the things we have. We have f of x to be x cubed minus x minus 2, x cubed minus x minus 2. We have that. We have the interval 1, 2. So we can say let x not be 1 and x1 be 2. Just in that. So choosing from that interval. So what else do we have? We have the tolerance limit, which is the stopping criteria. So it tells us when we should stop. So from here we can begin. So we know first of all that x1, if n is 0, so we know x1 is equal to x0 minus f of, no, that can't be. We already have x1, x0 and x1. So we're going to have x2 equals x1 minus f of x1 into x1 minus x0 all over f of x1 minus f of x0. So it means we need to do all the evaluations. So here now, we know that f of x0, f of x0 is going to be equal to x cubed, right? X0 is 1, so we have 1 raised to power 3 minus 1 minus 2. That's the f of x0. That is 1 minus 1 minus 2. And the answer is minus 2. And then we have f of x1, which is equal to 2, because x1 is equal to 2, right? So that's 2 raised to power 3 minus 2 minus 2. That is 8 minus 2 minus 2. And that is equal to 4. So, and those are the things we need, right? So we can then go ahead and say that x2 is equal to x1. X1 is 2. X1 is 2 minus f of x1, which is 4 here. So we have 4 multiplied by x1 minus x0. That is 2 minus 1 divided by f of x1, which is 4 minus f of x2. That's minus 2. Something like this. So x2 is equal to 2 minus 4. 2 minus 1 is 1. So we have 4 plus 2. Okay. Minus and minus is 4. Is plus rather. So x2 is equal to 2 minus 4 divided by 6. 2 minus 4 divided by 6. So that x2 now, I mean, we can find the LCM. So x2 is equal, or I mean, this is 2 minus 2 over 3. 2 minus 2 over 3. So x2 is equal to, LCM is 3. 1 in 3 is 3. 3 times 2, 6 minus 2. That is 4 over 3. We can leave it in fraction, but I mean, at some point, we don't have a choice than to go decimal. So that's 1.33. We can keep going, high precision if you like. So that goes. So we have x2 right there. So we now need to compare. Okay, let me stop at 3 decimal places. Okay, so now we have one of our solutions, x2. That's the first iteration. So how do we know if this is a good enough result? So we have to check. So we check uh, the stopping criteria. That's absolute value of x2 minus the one before it, x1, is equal to, so x2 is 1 point, x2 is 1.333 minus x1. X1 is 2, I believe. Yeah, x1 is 2. So, and this is equal to, it's absolute value, right? So that's just going to be 0.6667 or 0.667. Okay. And now this is, here we are going to have absolute value of minus 0.667. But because we don't care about the minus, so this is 0.667. So this is greater than the epsilon. This is greater than 0.01. So what do we do? Iteration continues. Iteration continues. Okay, because until this this absolute value is less than the stopping criterion, iteration has to continue. So we move on to the next iteration. So this is our first iteration now. First, okay, maybe I shouldn't name the iteration because the x2 and all that can be confusing. So let me go for the next thing now. So we now have x3. X3 is equal to x2 minus f of x2, all right, into x2 minus x1 all over f of x2 minus f of x1. Okay. So I mean, if you put all the values together, right? If you we know f of x and everything. If you put all the values where they should belong, we can just go straight. And so if you do this, this is more like x3 equals x2. Now we have found it to be 1.333, 1.333 minus f of 1.333. That means substitute 1.333 into this function, into the function, f of x equals x cubed minus x minus 2. Substitute it there, then into 1.333 minus x1, that's 2, all over f of 1.333 minus f of 2. So if we do that, our x3 is going to be 1.463. Okay, 1.463. And so then that is another result. But we have to check, is this result good enough? So we go for absolute value of x3 minus x2. So if you do this, x3 minus x2, that is absolute value of 1.463 minus 1.333. So that is roughly 0.1294 or something like that. Or 0, yeah, 0. Yeah, that's the rough idea, 0.1294. And that is, I mean, there may be some little differences depending on the approximation and everything that I am doing. But I mean, the result will be basically almost that. So, and this is still great. This is, what did I do the other time? Yeah, this is greater, right? So this is greater than 0.01. So it means we have not arrived. So what happens? Iteration continues. Iteration continues. Okay. So now we go for the next one. we go for the next one, which is x4. So we have x4 equals x3 minus f of x3 into x3 minus x2 all over f of x3 minus f of x2. Okay, now that means that x4 is equal to, we know x3 already. X3 is 1.463. So that's 1.463 minus f of 1.463 into 1.463 minus x2. X2 is 1.333. 1.333 divided by f of 1.463 minus f of 1.333. So you just substitute into the function, all right? And then you get x4 to be 1.53, 1.53, uh, 1.5312. Don't mind me, I'm not consistent with the decimal places, but I mean, it's better to make it to be consistent. Maybe take it to six, at least four decimal places. So that's x4, right? So the next thing is we want to check, have we arrived? So absolute value of x4 minus x3, that is absolute value of 1.5312 minus x3, which is 1.463, and that is like 0.0684 greater than, which is greater than 0.01. Okay, it's still greater than 0.01, although we are almost there, but this is still greater. So iteration continues, but we are hopeful because it's the value is getting smaller and smaller. I mean, that absolute value is getting smaller and smaller. So it means things are, so one day we will arrive at where we are going. So that's x4, right? So we can go for x5. So we can go for x5, which is x4 minus f of x4 into x4 minus x3 all over f of x4 minus f of x3. So again, we do all the routine. So x5 is x4, where we're coming from, is x4 is 1.5312. Okay, 1.5312 minus f of 1.5312 into 1.5312 minus, that's x4 now. X3 is 1.463. 1.463. Well, I should have said 1.4627, but it's okay. I mean, something like this. So we have f of 1.5312 minus f of 1.463. Okay, so x5 again is equal to so x5 now, right? X5 is equal to 1.5209. Okay, so again we check. So this is another result. So again we check absolute value of x5 minus x4. Okay, and that is equal to absolute value of 1.5209 minus x4 1.5312. 1.5312. So this is equal to 0.0102, something close to this. Now this is almost there, but it is still greater than 0.01. So iteration still continues. Iteration continues, but we're almost there, right? So we are hopeful. It's converging. That's what that means. It's actually converging. So now we go x6. So sometimes you'll be told the number of iterations to do, but if you're not told the number of iterations, you use the stopping criteria. So x6 now is x5 minus f of x5 minus into x5 minus x4 all over f of x5 minus f of x4. Okay, so x6 is equal to x5 now is our x5 the other time is 1.5209. So 1.5209 minus f of 1.5209. That means put 1.5209 into x cubed minus x minus 2. Then all of this into 1.5209 minus x4 before it. X4 was 1.5312. 1.5312 all over f of 1.5209 minus f of 1.5312. So if you do all of that, x6 would be something like 0.0005, so something this tiny now. Okay, no. No. X6, sorry, X6, I think I'm already jumping. X6 is 1.5214 roughly. Okay, so this is another result. So then we check the stopping criteria. Absolute value of X6 minus X5, which is absolute value of 1.5214 minus 1.5209, 1.5209. So if you check this, it's something close to 0.0005. Now, if you punch your own calculator, it may be a bit different from this, but it won't be far at all. So this is now less than 0.01. So here, what do we do? Here, the required result has been attained, attained. So the solution to f of x, which is equal to x cubed minus x minus 2 in the interval 1, 2, given epsilon equals 0.01, is x, which is that's the latest x6 now. The result that gave you this thing, that's 1.5214, 1.5214. Okay. Now, I mean, so in 5 iterations or so, we're able to finally arrive at the result. I mean, so for bisection, we had to just stop at some point and then go for Python code. So here we also we have the Python code. Somehow I couldn't put the Python code in the in the in the description box as I promised. So so you may want to follow it right from here. So this is the Python code for secant method, right? So I've improved the code to show us the number of iterations that gave the results. So view show line numbers. Okay, so we define the secant method in line 1. We do the iterations in all of these places. Then we have the conditional statements around line 5 and 6, and then at the end of in line 19, this is where we define the equation we want to solve. So if you are using something like this, you just go ahead and define any function you define here, it can solve it for you. And then the interval 1, 2, it has been put here. So if I just run this now, you see we get the results. I finally get up 5.311 like that within like 4 iterations. We have the initial condition already, so we just do 4 more iterations. I think in that case I did 5 iterations and we arrived at the results. Okay, so the final result is like 1.5213, which is roughly 1.5214, which I also got here. Yeah, 1.5214. So for those who are on Facebook, I'm able to put the code on Facebook, so it's fine. So you can check on Facebook and copy the code from there. Just put it into your own Jupyter notebook and run it. Okay, so that's how the secant method has been. It's been a very interesting journey. So please go through it. I did not bother expanding all the functions step by step because I had done it before now. So I just put the results. So please take your time and put the function. So the way you the use of your calculator here is really very important, especially in an exam or test condition. So you need to really practice with it. Don't get someone's calculator and go to the exam, or you can easily run into trouble because this is computation heavy if you have to do the iterations manually. But if you are writing the code exact, so in that case, that makes things pretty easy. All right, so this is the end of secant method. Thank you for listening. If you have not subscribed, thank you very much for doing that. If you have not subscribed, please go ahead and do that. Hit the notification bell so you can always get alerted each time a new video is released. And of course, if you have you can make a comment. Let me know if this is helpful for you. Let me know how helpful this is for you, and let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. And like and share so that more people can have access to this great learning. Till I come your way again, do have a great time. Bye.